Afternoon, everybody. Welcome to our seminar where we have our very own Réamonn Ó Buachalla, who will talk about spectral gaps for Dolbeault Dirac operators and irreducible quantum flag manifolds. Go ahead, Ray.
All right, thank you. So this is the first time I've spoken about this. It's been in the archive for a while. So yeah, see how it goes. I'll try to. The last time I spoke here, I gave an excruciating amount of detail. Lost everybody, so we'll try to go at a slower pace and not give. There's a lot of general theory behind all of this, but it will just get lost in a flood of definitions. So I'm going to present it in terms of the motivating family of examples, which for me, of course, are always quantum flag manifolds. So let's start with just a very quick, and again, given the mixed interests of the audience, lightning quick introduction to what Drinfeld-Jimbo quantum groups are. So let G, bracket G, be a complex semi-simple Lie algebra. If you don't know, when your Lie algebra is simple, semi-simple, a direct sum of simples, where simple is, what you think it should be. These can be classified. They can be converted into root systems. These can be classified, and they fall into four families: the A, B, C, D, and then there are five exceptions. They come from compact, connected, simply connected Lie groups, and this gives you an equivalence of categories between these two things. So why are we interested in this here? Well, this is a non-associative algebra, as I was just teaching the undergraduates. So that's difficult to deal with. So what do? We convert it into a associative algebra called the universal enveloping algebra. So we take this, turn it into U of G, and what is this? It's a quotient of the tensor algebra by certain things that turn this non-associative Lie bracket into an associative multiplication. This thing is good. It's said it's associative, so then you can look at just plain modules, not like Lie algebra modules. The representation theory of this is going to be exactly the same. All of these things carry over, so it's a nicer object to deal with. And what's more is that in fact, it is a Hopf algebra, which is great. We all like Hopf algebras. What is all of this Drinfeld-Jimbo quantum group stuff about? Well, you then can produce, and we'll define this, but as we say in Leningrad, when it was Leningrad, people working on quantum integrable systems discovered a Q deformation of this algebra, which is still a Hopf algebra. People like Reshetkin, Badev, Takhtajin, and as I was reminded in Cerny at the winter school, Sklianin as well, who did apparently a lot of the hard work, did one of the calculations of these things, discovered this amazing Q deformation, which has found a huge amount of applications since then. I mean, things like manifold invariant, the study of knots, applications, of course, back to integrable systems where it started from. Even things like von Neumann algebras, these things have started to appear as well. So they're mysterious, very beautiful, with a lot of structure. And well, it's been about 30 years, so that's relatively new mathematical terms. There are lots of things that we don't understand about it. So let me first, though, recall some things that we do understand about them. And I should call this, of course, is the Drinfeld-Jimbo quantized enveloping algebra, for which Drinfeld, of course, won the field, and for Jimbo did. But what properties or what things do we know about it that are well behaved? Well, if we take the category of UQ of G, I'm going to put a small mod here because this means finite dimensional. This thing is equivalent to the category of finite dimensional modules over U of G, which is of course the same thing as finite dimensional modules over G. So that's great. The representation theory stays the same, which is one of the amazing properties of these things. So in fact, so if the representation theory all stays the same, then what is kind of fundamentally different about these things? What's fundamentally different is that this equivalence is not monoidal. Not okay. The fusion rules of this. If you this category is semi-simple, so it's every object inside there is going to be a direct sum of simple. And then when the fusion rules, as you would describe them, when you take two irreducibles, when you take two modules V, and I tensor them, the lambda and the mu, this is no longer going to be irreducible, so then this is going to decompose into a direct sum. Theta's, let me call this. Okay. This is what we would call the fusion rules of this category. They're actually the same. So it's a weird thing. It's actually when you try to take the obvious monoidal equivalence between these two categories, it doesn't work for real reasons that you initially think the kind of conditions you have for a monoidal equivalence or category theorists being annoying, but actually no, they do know what they're talking about. That this is actually the same, but it is not a monoidal equivalence. And then to give you some way of where the hell does this deformation come from and why is this special? Well, basically, if you want to find a category which with a monoidal structure that's going to be equivalent to, as a category to this, and whose monoidal structure gives you the same Grothendieck group, which is to say you have these same fusion rules, then it turns out that there's a one parameter family of such objects. And that is this category here with this tensor product, which is the usual tensor product. There are different ways to realize this category, which is to say there are different Q deformations, but you will always get the same category. So to some extent, what we're studying, you've got this unique deformation of the category, the monoidal category, and we look at these things because they're a way to realize it concretely. Okay, that's why these things, that's one sort of general way to see where the hell is this deformation coming from. Good. No, well, we do understand a lot of things like this as some of the representation theory and so on. Something that we do not understand is this piece I'm talking about up here. So if we take complex semi-simple algebra, and then we're going to go up to the universal enveloping algebra. What we've found in the quantum setting is we've actually started with the universal enveloping algebra. So of course, one would want to find some E that lives inside here. Analogy. This we do not understand. Sorry. There does not exist. What does that mean? By not exist, I mean there is no generally accepted notion of Q the algebra. There are various approaches to this, notably the approach of Majid with braided the algebras and so on, but it's definitely not something that people consider accepted, and there were lots of questions to figure out what's going on here. And this, I guess, is sort of what I'm going to talk about today. You're asking why we're looking at all of this non-commutative geometry of these things. That's kind of one of the questions we're really trying to answer. To bring geometric intuition towards answering questions like this about the structure of the enveloping algebra, the quantized enveloping algebra itself. Okay. And less so about fitting it into some sort of a general framework or a project of non-commutative geometry in general. No, what we do have though is embedding So what do I mean by this? You have for any semi-simple Lie algebra, you're going to have the so-called triangular decomposition. If you think of it for SLN, these are the trace-free matrices, special linear algebra. This is basically the H, your cartan, is going to be on the diagonal. This is the upper, strictly lower triangular matrices. There's the nilpotent algebras inside there. So what we do have, though, is an actual embedding of this. And what's going on a lot of the time with the Lie algebras, or the Jimbo quantized enveloping algebras, is that it's the torus, the Q deformation of the torus, that makes everything kind of complicated. Because to some extent, this process of going from this to here involves an exponentiation of the torus and so on and stuff, and so on and so on. It's also the torus that deforms the coproduct, which is the thing concretely that deforms the monoidal structure, and so on and so forth. But this thing in the quantum setting is a lot better behaved than the whole Lie algebra itself. Okay. And of course, I should say that this, bring it down here. Who is this due to? None other than famous Lustig, George Lustig, who constructed such a thing in order to give a quantum PBW theorem. Which went on to many. A PBW theorem, for those of you who don't know, is basically a canonical or a very natural basis of this algebra constructed from root vectors, which is to say in the classical case, when you take G, it decomposes into weight spaces. These are eigenspaces with respect to the action, the adjoint action of the torus. And you take these vectors inside here, and from these very canonical elements inside in the enveloping algebra, you construct this basis of the enveloping algebra itself. And it's a fundamental tool in the study of universal enveloping algebra. So what he wanted to do, what Lustig wanted to do, was to look at this and go, well, do these things exist in the quantum setting? And for that, he had to invent these nilpotent quantum, nilpotent Lie algebras and corresponding root vectors. And he said it did. And then this had a huge amount of applications, and it's kind of a milestone result in the theory of Drinfeld-Jimbo quantum groups. One thing, for example, are canonical bases. And canonical bases are one of, talking about the applications of these things at the start, what I didn't mention was the applications to classical representation theory of Lie algebras. Classical ones, it turns out that this PBW theorem gives you this amazing basis of these representations, which has huge applications inside in classical representation theory, ultimately leading on to such fashionable things like categorification. But anyway, Poincaré, PB, Bott, and Birkhoff. Sorry. Yeah. With it's yeah. It's Vit, yeah. Poincaré, Birkhoff, Vit. Okay, no, what I said is we're trying to understand a lot of these things. Let's bring some sort of a differential geometric philosophy to bear in these things. So what is this classically? This guy is isomorphic to, well, actually, let's take the sum because we'll be considering all of it today. Is equal to the tangent space of the full flag G. Call this for the rank, okay? So inside in any one of these the corresponding Lie groups, the compact connected, simply connected Lie group, 2G, you've got a torus inside there, which is dual in fact to the cartan that we have inside here. And then if you quotient by that torus, you get what's called the full flag. And that's actually the tangent space of these things. So the simplest example here would be for SL2 and SU2. Then when we quotient SU2 by the torus, full torus, which is just T, we get CP1, which is just S2. So then you can start to treat these things as quantum tangent spaces and then see if we can build up a geometry, a quantum geometry for these things. That's something I've spoken about before. We're going to specialize now today to the case, not of the full flag, but of the Grassmannian, which lives inside there. So again, this is like the Grassmannian of one planes, a very special case, CP1. So what instead we're going to look at taking inspiration from this.
Réamonn,
Yeah.
I have a question.
Yeah.
Yes, sorry about that. When you say n plus and minus, that will be like the holomorphic and diholomorphic, am I right?
Exactly.
Okay,
Yeah.
thank you,
Yeah.
sorry.
The almost complex structure from these things comes from the triangular decomposition of the corresponding Lie algebra.
Right, so technically that's not really the tangent space, right? Because, I mean, it's like,
It's the complexified tangent
I
space.
am sorry about bothering
Yeah,
you.
yeah, sure. No, you're completely correct. It's the
Okay.
complexified tangent space because for me everything is over C.
Sure, thank you.
No. So instead, let's look at. No, we want to look at non-full flag. And in particular, let's just take it for the sake of time and not giving you details that we don't have time for. I'll just discuss, sometimes I'm going to specialize to the A series case, which is to say the case of SLN, which is to say the case of SUN. But what I'm doing can be extended to the other series in a way that I will say a little bit more about in a while. We want to look at Q flags. So then what do we do? Grassmannian. So how do we define the Grassmannian? Quantum Grassmannian. Take X here to be, X will be the correspond classically to the dimension of the planes that you're looking at. So when this is, for example, 1, you're going to get back CPN. So what is it? It's the subalgebra. L, where L is going to be the rank. All right, we've just taken a subalgebra of the enveloping algebra. So what maybe I haven't explained here is this guy is going to be these are the corresponding simple generators for this part. The F's are going to be in the negative. And of course, this is classically at least living inside of the cartan. No. What we can now do from this this would be, so what am I introducing to this? But this is the Lie algebra classically, or the universal enveloping algebra of the Lie algebra of the corresponding subgroup of G whose quotient will give you the Grassmannian. Okay, so we just remember this, that GR classically and is going to be isomorphic to SUN over SUM times UN minus N. Okay. Now, what we now do is we're trying to look for a analog inside in this enveloping algebra. So here, this is from the work of Lustig. We see what it should look like for the full flag. We want to look at the corresponding thing for the Grassmannians, which classically would actually live inside here. So we're going to look for some sort of a sub-tangent space that this thing should have. What do? Well, you just take the classical definition. In fact, take the obvious analog. We take the corresponding simple generator. This X, as I said, it's varying along the generators of the Lie algebra. And this is the one that you cross. This is the one that you pick out dependent upon the dimension of the planes that you're looking at classically. Take this, F, and this is F sub X. And classically, in fact, this thing, even though this is infinite dimensional, a lot of, and this of course is the adjoint action. the Hopf algebraic adjoint action, which classically is just the adjoint action. These two things turn out to be finite dimensional, and this is a direct Q deformation of the tangent space of the Grassmannians classically. And this is in fact, so, well, does it satisfy any properties? Well, in fact, it satisfies this when you take the co-product of these things, plus C, then you end up in T plus C tensor UQ of SLN, or more generally, the irreducible flag manifold. And the fact that this is a coalgebra allows you to do a lot of stuff. And this is sort of a quantum phenomenon, or the accident that you need to check actually works. And so this thing is a genuine Q deformation of the tangent space, of the complexified tangent space of the Grassmannian. And this is really what we call the Heckenberger-Kolb tangent space. I'm giving you this here for the Grassmannians. This is a special case. In fact, this generalizes to all quantum irreducible flag manifolds. And what are the irreducible? Classically, you would take flags, which are going to be something again, whose correspondingly algebra looks like this. This definition is general, but not choosing just one X that you're omitting, but a subset that you're going to omit. And then these are symmetric spaces. And here is irreducible. These are symmetric spaces. Another, probably the other nicest family of homogeneous spaces classically. And when you take the intersection, you get what many people would call the best manifolds ever. And it's true, they're amazing. And this amazing behavior actually carries over to the quantum setting, where this search for, again, coming to try to ultimately solve this property or this question here, to investigate the structure of the quantized enveloping algebras. These submodules, these finite dimensional submodules that are direct Q deformations inside there, are amazingly well behaved. And we're trying to examine these things with geometric questions and geometric structures in order ultimately to get back to them. And as I said, there's no reason to consider just the irreducible flags. Using sort of Lustig, we can go up to all partial flags and so on. But these are the ones that were discovered first in this amazing classification result of Heckenberger and Kolb. And they're the ones for which a lot of nice things happen and stuff that I won't be able to discuss today, but that allows a lot of the things I'm going to talk about to actually work. And yeah, the extension to the general flag is, of course, a goal for the future and work in progress. But not for today. So this is tangent spaces. Well, from a tangent space, we actually like to do some geometry. We'd like to build up from this Q deformation of the associated Dirac complex, the Dirac complex of the Grassmannians, or more generally, these irreducible flag manifolds. So for this, you'll need to recall a little bit. These are the enveloping algebras. We can, of course, consider a dual Hopf algebra. This is the Hopf. Every Hopf algebra, there's a natural way to construct a dual Hopf algebra. There are some subtleties involved because the co-product doesn't extend in the obvious way it should. So you have two choices. Either you restrict the functions of the dual, or you take completion. I guess the Feaster algebraists will take a completion, the algebraists will restrict to the Hopf dual. That's what this is. There is unfortunately a subtlety because of this exponentiation I spoke about before, that we get representations that we don't want. So Hopf dual here should be in inverted commas, but okay, we won't get into those subtleties today. It's just the natural Hopf dual. And you can think about it basically, if you know what this is, that the Peter-Weyl theorem. You can kind of take the Peter-Weyl construction. That's a concrete realization of this Hopf dual procedure for the special case of these guys. And now So this was, as I said, this is just the quantization of the enveloping algebra. This is the quantization of the enveloping algebra, of the Lie algebra, of the thing that we're quotienting by classically to get the flag. We would like a Q deformation of the algebra of functions, something that lives inside here. And we do that, wrong side, by just taking the action. So because this is a dual, we can use the coproduct and we get a natural action of the enveloping algebra on this. And this. Precisely our coordinate function in a flag manifold. Okay. No, it turns out that, and as Q is equal to 1, this gives back the algebra of algebraic or representable functions G on the classical flag. Okay, the direct Q deformation. This works for all flags for any subset of nodes, not just the irreducible ones here, the interaction with the symmetric. So we now would like to see, classically the Dirac complex is this differential graded algebra, which is a module over the algebra function. So we'd like to construct some sort of a differential graded algebra, which is a module of functions over these things from this tangent space. And in fact, this property here that I described, I guess there were two. There's the finite dimensionality, which is maybe not, which is definitely not clear and assured. So up here, right here, this thing, which is classical dimension. And there's the fact that it satisfies this coproduct. The classical dimension means that you've got a Q deformation of something classical. There are no extra dimensions. All of these things match. The coproduct means that construction I'm about to write here actually works. So now what do? I take OQ of G. I take a cotensor product. This. And this is the dual module, I guess. Because we're looking at cotangent vectors. So this is the cotangent space, not the tangent space. We have to dualize this. What does this mean? This is basically the Hopf-algebraic generalization, classically, of an associated vector bundle over a homogeneous space. So if I've got some G over H, homogeneous space, then I can construct a vector bundle over this for any H module. I can quotient over the representation in the obvious way. So this is how you take a representation of the group that you're quotienting by, and from it produce a homogeneous vector bundle. And this is a direct non-commutative generalization of this. Now we have a map. So in addition to this, so this gives us a direct Q deformation of the module of sections, the projective module of sections of omega 1. We also have built in a map that goes from OQ of G LS up to omega 1 Q of G over LS, which satisfies the Leibniz rule. This is part of a much more, part of a general construction of these objects for quantum homogeneous spaces coming from these quantum tangent spaces. But basically, we'll just give it the explicit, we'll give it in terms of these explicit examples that we're treating. And it's this condition here that allows everything to work amazingly. So far so good. We've got a Q deformation of the one forms. What about all of the rest of them so that we get a complex? Well, that's actually quite easy. There's a formal process, again, that I'm not going to go into because that's not what we're really specializing to. But we have a maximal prolongation. This is a process that works whenever you have a module a bimodule together with the map from the ring, the algebra, to the bimodule, satisfying the Leibniz rule, there's a maximal there's a maximal way to extend it, and the maximality is sort of a universal property that defines this thing, and it works in quite some generality. So that's what we do here. So we take omega 1 of q of g, of g over LS, and bring it up to and this thing is, of course, a differential graded algebra. And it's a Q deformation of the Dirac complex of G over LF. So, look, coming directly out of the algebraic structure, these kind of sub co-ideals, finite dimensional modules and co-ideals that actually naturally live inside a new QG, even though we don't understand the whole picture of what the Q Lie algebra should be, we do have lots of things, kind of partial versions of it for all of these different flags, for different subsets of nodes of the corresponding Dinkin diagram that we're looking at. And in fact, there's quite a natural and very well-behaved genesis, or I guess beginnings of a differential geometry. So in particular, we see that we have associated differential graded algebras. So giving us this means possibly of using geometric ideas to probe the structure representation theory of these quantized enveloping algebras. All right. No. Classically, flag manifolds are Kähler manifolds. What's a Kähler manifold? It's something that's a complex manifold where, it's an almost complex manifold coming from that decomposition that Rita was referring to, the holomorphic and anti-holomorphic. That, of course, is integrable. So in Nuremberg, you have a holomorphic structure, and it has a Riemannian structure, and these two things interact in an extremely nice way. That's what a Kähler manifold is. So, because that's such an important part of the structure of these things, when we're like, is there in particular a Riemannian metric that we can put on this? That is a long question, something that took a long time to actually sort out. And I'm going to summarize it all in one line. I guess, I don't know if I can call this a theorem because it's kind of a collection of theorems, but I'll do it anyway. And this is, as people tend to do these days, I'll write many hands. This admits a OQ of G covariant. So again, I should mention that by the construction of these things here, this object actually lives inside in this category of relative Hopf modules. So, which is the natural non-commutative generalization of the category of homogeneous vector bundles over it. So it's actually equivalent, right, this Takeuchi equivalent to the category of modules over, this side, over UQ of LS, over the Levy. So it has a coaction and an action of the module at the same time, and they interact. Okay, the module here is, as I already said, this is the bimodule that's coming from the structure of this here. But it's the left module, and then it's the right module by operating on the right here. But it also has a coaction, basically by this construction here, and it's just the coaction, the co-product restricted to this here. Okay, so then whenever we're looking at something and putting some extra structure, particularly like a metric, we want this to actually interact nicely with this comodule structure, which is to say we want everything to be covariant. We want things to be comodule maps in the appropriate sense. Q deformation. Of the Houdini study metric of the classical Riemannian. What's the Fubini study metric? If you think about all of these things are projective varieties, so they embed into projective space, CPN. That's got this very canonical metric called the Fubini study metric for the case of S for CP1, S2 with the round metric, for example. So when you send it into CPN, you can restrict this down. And this is what the Fubini study metric, and it's the natural Riemannian metric for these manifolds. And basically, through a lot of work, I should mention there's work of myself with also work of Marco Matassa, I would say, in particular, there's two names. This works in an extent, okay? But to be careful, there are things that a lot of things that we still don't understand about the structure of this, and some tricks we have to use, some analytic tricks we had to use. And what happens is that forces us to assume that Q lives in a small enough, it's around the origin. 1 minus epsilon, 1 plus epsilon. Of course, once it has to extend to all real Qs, almost certainly, but we'll need to have a better understanding of the internal structure of these things to actually be able to extend it. But for the moment, it does work for this. Okay, that's one important caveat. And we'll just denote this by G. This is what a Riemannian metric globally will do classically. If you just want this to be the metric and you forget about the positivity, then this works for all Q except for a possibly finite set. When you bring in the positive definiteness, that's actually where things become more complicated, and then you have to restrict to the small interval around 1. Okay, and then we can build upon this to produce an inner product, which is equal to H. That's the definition after G. And what's this? It's the Har. The Har of OQ of G. The Har, the corresponding compact quantum group, if you want. Which classically is just going to be integration, the functional that integrates any function with respect to the Har measure. But it has a direct non-commutative generalization, and then that together with the positivity of this gives you an inner product. Now, what happens, sorry, I've gone a little bit in the wrong order, but what I didn't mention, but I still have space here, so everything is okay. The decomposition, no, but I don't have space because I need to draw a big diagram. The decomposition of this into our two parts, this UQ that we have still up here, UQ of LS by EX and UQ of LS by FX, this T10 plus T01, decomposition of the holomorphic and anti-holomorphic, as we were saying. This gives us a corresponding decomposition of the calculus, the first order calculus. Which in turn gives us a decomposition of this thing, of the whole calculus. And it ends up decomposing, just like in the classical case, the sort of diamond structure. So let's write this very quickly. Where for just an ordinary Riemannian manifold, an ordinary differential manifold, your differential graded algebra is just a complex. Goes up. This decomposition into one forms this almost complex structure, allows you to decompose it into a diamond. Let me just give a picture quickly for what happens in lower dimension. The example here is just the dimension. So you would have omega 0, 0, which is just your functions. And then you'll have omega 1, 0, 0, 1, this decomposition here. And then we go for the next. Then we go up here. This is omega 2, 1, omega 1, 2, omega, wait. Yeah. It's 2, 0. Yeah, yeah. 0, 2, then this becomes 2, 1, and this becomes 1, 2, and then this becomes 2. So in fact, because you got an exterior, classically you have an exterior algebra construction that doesn't continue up here, it collapses down. And this actually carries over to the non-commutative setting for all of these. This is just what it is. What's important, what I'm just about to say is that the exterior derivative of the differential graded algebra, the D, will decompose as a direct sum. So this decomposition is what would classically be the almost complex structure, and then this decomposition of the exterior derivative into these two parts that I'm about to write is actually equivalent to integrability of the structure, which is to say that it's not just an almost complex structure, but something that comes from a genuine holomorphic structure on your line calculus and so on. And this is a double complex. Okay, what does that mean? It's the natural generalization of a differential graded algebra to a bigraded. Means that if I continue along twice, whenever I square one of these, I'm going to get 0. And if I go around any of these diamonds, these small diamonds that compose a bigger diamond, going one way or the other will differ by a sign. Okay, they don't quite commute, but they commute up to a -1. Now, these guys admit with respect to the metric that I've defined up here, it turns out that this exists, i.e. del and del bar are adjointable. Let me use the star. Usually I use the dagger because there are too many stars around, but at the moment this doesn't matter. Adjointable. Then that allows us to introduce an operator and these are our Diracs, Dolbeault Dirac. Okay. So, classically, at least over a complex manifold, this is what Dirac operators are, up to a twist by a line bundle. Is something we're going to come back to pretty soon. Here, I mean, here, I'm just being lazy. No, this is. Yeah, this is all Q's everywhere. Yeah. I mean, this is the decomposition in the quantum case coming from this decomposition of the tangent space, which is a decomposition by construction, I guess. Yeah, and for Q is equal to 1, this is the spin C, at least, Dirac operator. There are some subtleties about these things, but these flag manifolds are spin manifolds, or at least spin C manifolds, and there's spin manifolds when this guy here is an even line bundle, which means you can take a square root, and then if you take the square root of this and you twist these things, as I'm about to explain, by a line bundle, you're going to get the actual Dirac operator of these things. So that's fine. Starting from representation theory, we've constructed actually a lot of geometry of these things classically. So the question one now could ask is, of course, look at some of the analysis that's involved in these things. And what the people who look at the more analytic, theoretic approach to non-commutative geometry do is they want to look at the properties of these unbounded operators. So they're operating on this Dirac complex, but of course we have an inner product, so we can complete that to a Hilbert space and then These things become densely defined unbounded operators. They're essentially self-adjoint. They satisfy all of the properties, in fact, of a spectral triple, except for the spectrum. So to give spectral triple in the sense of Kahn's C-star algebraic K-theoretic notion of a non-commutative Riemannian manifold, we need that the eigenvalues either of them will give you a spectral triple. The eigenvalues lambda go to infinity, and that the dimension of the corresponding eigenspace is fine. Okay. That's a very difficult question. Unfortunately, up until now, the only way that people have had of verifying things like this is the eigenvalues that should explain these operators because of symmetry reasons, because of Peter Weil, are actually diagonalizable. So your Hilbert space admits an orthonormal basis, and these are the eigenvalues of the orthonormal basis. And of course, it's countable. It's a separable Hilbert space. The only way we've had of actually showing that these conditions are satisfied is explicitly calculating the spectrum, and that's a nightmare. So trying to come up with some more conceptual way of doing this, general, again, a very difficult problem, which is why I gave it to Arnav for his PhD. Let's see how that goes. But what I want to talk about in the time that's left is a way to get around this by using a lot of the differential, complex, and Kähler geometry that we have here, so that we will not need to do any explicit calculation of these things, these terrible explicit calculations. So I can't do it explicitly for this, but if we twist by a line bundle, magic things happen. Okay, so I'm not too sure how much at the time. So what do we do in this? In fact, over each OQGLF, we have an O of U1 Hop-Galois extension. Basically, it's like a torus bundle. Classically, it's a torus bundle over these things. And this O of U1 Hop-Galois extension, that's basically the Hopf algebraic generalization of this notion. For those of you who are more C-star algebraic, and we're looking, let's say, at Sophie's talk last week, at least for the case of CPN, and we expect more generally, is what we're working on, Sophie and Karen and myself, is that right here, OQGLS, and we put a little s up here. This is for semi-simple part of the Lie algebra as opposed to the general reductive one, if that makes sense to you. Then the C-star algebraic completion of this should be a graph C-star algebra. In the case of, and indeed it is, which should be, this is our conjecture at the moment. And actually for the case of CPN, this is known. So you get CPN, and this embeds into OQ of S2n minus 1. So what is this bundle, this O of U1 principal bundle over CPN, this special case? It's just the odd dimensional sphere. Okay, and these are graph C-star algebras. And what happens is that this one, with respect to the gauge action that you have, the gauge action that you have in any graph C-star algebra, the invariant part will be the C-star algebra completion. Again, there's basically a canonical C-star algebraic completion coming from the C-star algebraic completion of OQ of G. Inside here is the flag itself. Okay, so maybe if we're more C-star algebraically inclined, that's one way to think about it. But the important part for us is that these guys decompose as a direct sum, up with the S, of modules over the flag manifold itself, this without the small s upstairs, for K, an element of Z. And these are Q-deformed line bundles. Okay. They're cued deformations of the projective module of sections.
Quick comment, I guess even though we don't know that for sure that they're going to be graph C-star algebras, at least it will be Kunz-Pimsner C-star algebras.
Yes, yeah.
And the gauge invariant part will again be the flag.
That's on my notes somewhere, but I wasn't reading carefully enough. Yeah, thank you. There will be Kunz-Pimsner, and then yeah, it's the invariant part to degree 0. And these line bundles here, if you take 1 or -1, I guess these would be the generating Hilbert bimodule for the Kunz-Pimsner algebra. So why are we interested in these? So that's fair enough, all of the algebraic stuff. Whereas the geometry, well, in fact, just like in the classical case, you take the definition from a geometry book, we can twist these operators here, these Dirac operators, by any vector bundle, which comes together with a connection. So in particular, by a line bundle. But needs a connection for each. Okay, this is, I should mention, work with Karen, myself, Andre, who's not here, Peter Somberg and Freddie Diaz. But each comes with an OQ covariant, co-invariant connection. Actually, it's with a unique. So what is a connection? This is just basically how you classically, when you have sections of a line bundle, when you have sections of a line bundle or a vector bundle over a manifold, you want to be able to differentiate them. There's not any unique way to do this, so you have to make a choice, and this is a connection. It's a linear map satisfying the Leibniz rule. Tensor B plus B Adler. And these guys come with the direct Q deformation of this. And in fact, moreover, they split up. Do we need this for the moment? No. And then this, basically the twist is with reduced map omega bullet Q dot S by Q, tensor the line bundle to itself. So we're going to twist the vector bundle or the projective module. And this is, of course, always over B. B is just shorthand for the algebra functions on the Grassmannian because they don't have space. We're twisting the vector bundle, we're twisting the modules non-commutatively, which corresponds to taking tensor products of your vector bundles classically. And then what do? We define then map. Going to go from omega to E maps to now, sorry. This is just a sign term that we need to include in order that everything is well defined. Classical recipe for twisting the forms by a vector bundle with respect to a choice of connection. So now we can do this here, and this actually allows us to twist our Dirac operators as well. So because of time, skipping a little bit of the subtleties here, but you see we've twisted it. So everything I've written here actually also works with respect to the splitting into the holomorphic and anti-holomorphic parts. Okay, so this gives the twisted Dirac. Okay, just by using the connection, or using the connection to the decomposition of the holomorphic or anti-holomorphic part as is appropriate. So then what we can do, I mean, we can do it up here as well, I guess that's the definition. We can take the square of this, we can take the square of this. No. This is what's called the corresponding Laplacian. This. Okay. The Laplacian is by definition the square of the corresponding Dirac operator. Now, if we're in the untwisted case, then it's a resultant Kähler geometry, and that carries over directly to the non-commutative setting, to the quantum setting, that your two Laplacians actually coincide. And this is kind of one of these miracles of Kähler geometry, which tells you that your Dirac cohomology can be refined by Dolbeault cohomology, this terminating with spectral sequences on the first page, and so on and so forth. But in the twisted setting, both in the quantum and the classical, this no longer happens. You actually get a curvature term that comes in. So this is what's called the Q Akazuki-Nakano identity. And this is with myself, Jan Stobicek. And Adam and Christian van Roosmalen. Part of the Coulter vanishing paper tells us that the difference between these things. Wait, so let me actually. Equal to this is the okay. So these are two Laplacians coming from the two Laplacians that we have coming from the decomposition basically of this thing into the complex and the holomorphic and the anti-holomorphic part. And then they differ by this strange thing here. What does this mean? I don't have time to explain to you, but this is actually a much easier object than these things are here. It's actually a module map, whereas differentiation, of course, is not a module map because we have the Leibniz rule, but this object is. Why is this important? Because these things are diagonalizable, and because this operator was so much nicer, I should mention, this, of course, is just the curvature of the connection on these things. And this thing is so-called contraction by the Kähler form. This very special form that lives inside an omega 1,1 that I haven't mentioned until now, but is actually the thing from which you construct the metric. And this result that I give a very brief presentation of. So, and this is what happens classically as well. So because these are Kähler manifolds, the extra structure has an associated 1,1 form, this form in the middle, that governs a lot of the structure of the Kähler manifold in both the classical and the quantum setting. This result here is very related to the representation of SL2 that you have on any Kähler manifold. But more stuff that I can get into. What happens though is that these operators, as I said before, the Diracs are diagonalizable. They admit the corresponding Hilbert space, admits an orthonormal basis of eigenvectors. That's the same for both of them. And in fact, one can show that all three, and hence, of course, this thing is diagonalizable. Well, okay, I have all three. What am I trying to say? I'm trying to say that all three of them are simultaneously diagonalizable. So this is a positive operator and this is a positive operator. They're self-adjoint basically by construction. As you can see over here, Twisting doesn't change that. There's still self-adjoint. So any eigenvalues will be either 0 or positive. Okay, elementary spectral theory. So if we could show that this thing, the eigenvalues of this were positive, then we would know that the eigenvalues of this had to be greater than 0. It turns out that this thing is a constant on chunks of these guys. In fact, it's going to be a constant on that. This, I should stress as well, though, what we're now doing for reasons classically motivated about the fact that the Dirac operator associated with the spin structure, when you twist it by an appropriate line bundle, this part here, twisted, this is isomorphic to the spinor bundle. As a result of its here classically. Not going to because seconds definition. And on the various chunks of this here, this thing acts as a constant. Constant changes as k goes, but that doesn't particularly matter. So we see then that this constant, theta, and this is strictly greater than 0. So this is, I guess, a theorem. And the proof comes from the Borel-Vey theorem, which I proved with Freddie and Ale during their time here. But this Borel-Vey theorem, so there's quite a bit that's going on with the application of this. And it turns out that it's related to the fact that, and sorry, this is for k less than 0. So for the negative line bundles, this turns out to be a constant. That's related to the fact that classically these line bundles in the negative case are what are called, well, they're negative line bundles, which means that their curvature is related to the scalar form by an appropriate sign. Okay, it's a scalar multiple, and the scalar multiple is a purely complex scalar multiple, and that has to have an appropriate sign, and whether that sign is positive or negative is by definition classically that the bundle is going to be positive or negative. It's the same thing as the algebraic notion of an ample or anti-ample line bundle, which is actually the thing that allows you by the Goodire embedding theorem to give you an embedding of your Kähler manifold into CPN, which is to say realize it as a projective variety. So there's a lot going on here, but we don't actually need to calculate this constant explicitly. Don't have time to explain the argument, but the positivity implies vanishing of certain cohomologies. And because of the Borel-Vey theorem, which gives us the cohomologies in the degree 0 of these things, we're able to basically rule out certain examples, and we're forced in the end, we can find that this constant is 0, which is to say that these line bundles are positive or negative. What does that mean for us with respect to the analytic properties of these things that we're looking to solve? Well, it tells us, as we see, that we've got a lower bound for the spectrum, and that lower bound is given by this guy here. Okay, so corollary of this, and this is self with Peter Sundberg and our old friend Fischer of Das. This tells us that the spectrum, so I should say as well, these operators are quite, well, they're unbounded operators, and they're not that nicely behaved, but their spectral theory is reasonably nicely behaved. So they have what's called point spectrum. So all the elements of the spectrum are actually eigenvalues. So the spectrum of this guy, and of course, when we have behavior about the spectral behavior of the Laplacian, then because it's just a square, we can conclude information about the spectrum of this. So it means that the spectrum of this guy, in fact, contains inside in this. So we have a non-zero lower bound. For the spectrum, which is called, in the classical literature, of course, a spectral gap. The gap being the space between 0 and theta. So basically, by sort of general geometric arguments, taking things like this Akazuki-Nakano identity, this particular type of Weitzenbach relationship between our eigenvalue or Laplacian, and taking things like notions of positivity for vector bundles, the associated concrete input of the Borel-Way theorem for vanishing and non-vanishing of cohomologies, we're able to actually conclude that this operator has got a spectral formula without actually ever needing to calculate anything. That's not completely true. So here, I guess the Borel-Way is the input. That's where we did calculate something. We calculated the dimension of cohomology groups. But I guess we're getting spectral behavior, information about the spectral behavior of these operators from the Borel-Way theorem, which is like a non-commutative geometric representation result. So it's quite nice, we feel. And then just as one last result, what about this? So there are these spectral triples and so on, and this is far too weak to tell us the spectral triple requires that our eigenvalues have got finite multiplicity and it can't have any accumulation points. So this rules out 0, for example, as an accumulation point, but certainly no way that we can conclude anything about the higher growth from this. But what we can do from this is that corollary is that this guy, I wrote it for the Dolbeault, but the same thing happened. Well, no, but this is a unbounded Fredholm operator on and this is the Hilbert space completion. With respect to this inner product that we introduced a long time ago. So, moreover, actually, we can even, so what's an unbounded Fredholm operator? You know what a Fredholm operator is, that the thing should be closed. That's basically the initial, the other thing that you need to take care of with respect to unboundedness. But if it's Fredholm in particular, it has an index, and then we can calculate the index actually using this Borel-Way theorem again, together with an application of this Akazuki-Nakano identity. Is equal to the dimension of the corresponding, this is the fundamental representation of G with respect to this choice of root, this X that we described in the end. And then one can calculate this, for example, using constant formula. I think it's constant. What is it say? Yeah. So this is just the standard formula because we know that the dimensions of these representations are carried over. So this is what this is explicitly. Again, this is the, I think, a constant formula. Usually with these things, constant is a safe guess. So one can actually use, again, the representation theory, the Lie theory from this to actually explicitly calculate the index of these operators in any case that you're interested in. So I think that's probably where I'm going to finish. And maybe just in summary, idea was that these tangent spaces that live inside an UQG that we're trying to examine was, try to take a geometric approach to looking at these things. And when you do, you have a huge amount of stuff that actually comes out of it. You have this Dirac complex that you get for free out of this. You have the corresponding vector bundle and connections that you can twist. You can then look at the corresponding operators even, and you see that the analytic behavior of these things, their spectral behavior, is actually molded by the underlying complex geometry of this differential graded algebra you have, and then ultimately connects back to the representation theory of the quantum group itself. So yeah, this is set as just for these irreducible flags. So one would want to extend after this to larger classes of the partial flags, not just the ones that are in the symmetric, connecting again with the work of Lustig and ongoing stuff. Try to use geometric ideas to examine these things, but that's where I'll stop. And thank you for your attention.
in the audience.
I have a question.
Okay, Alec, go for it.
Yeah, right. Thank you for the nice talk. I was kind of surprised to see that in order to do the twist, you don't use any bimodal map associated to the connection on the line bundle.
Yeah, that's true. I mean, they probably are all bimodule connections, as we would conjecture, but yeah, it doesn't come into it at any point.
I guess it doesn't appear because you are multiplying by the line bundle on the right.
I guess.
Might be.
Why would it come into this?
Yeah, would it come in if...
No, but I mean, if you multiply on the left, it works as well. You just actually it becomes simpler because you remove this sign.
Right, but these are all left bimodal connections. Yes, they are all left connections, right? So if you multiply by the left, you have to flip the line bundle and restore the differential calculus at a certain point.
You can turn them into right connections as well, I think. It's a good question. But I mean, okay, everything does
work.
I mean,
I guess my question is if you have thought about this, if the results here hold, even if you, I mean, you do the twist taking in account that you have to use the bimodal map.
I would guess, I'm not sure. No, it's a good question. What does the bimodule properties of bimodule map, what role does it have to play? Because in these things, I don't even know about boundedness of these things in general. I'm not sure, actually. No, it's a good question, but I'm not sure.
Right, okay, thank you.
Yes, I think you had a question.
The sum of line bundles above. Yeah, this one. Does this one also come from diagonalization of a certain operator on OQ? So are those EHs can be identified with eigenspaces of a certain differential operator?
They don't know. I mean, they're eigen. You've got a U1 coaction on this, I guess, which is the same as the Z grading. Differential operator? No, I don't know. Some sort of an SL2 representation. I don't know. No, I don't know.
Other questions? I have a question. So you want to push this past the irreducible, guys? And where is like the hard part in that? What piece are you missing somehow?
There are two.
They're not irreducible, they're still Kähler, classically?
Yeah, absolutely.
Okay, so you expect this to be the case?
This is, I guess, what's the problem? So not that, okay, well, we need to actually construct these tangent spaces, these quantum tangent spaces for a start. But this is, well, the paper should hopefully appear sometime in the next month, at least for the A series. This is done for the case of SLN. So we do have that and then you take the construction of the differential graded algebra from the tangent space. This will work almost certainly. We need to verify the dimensions, but these are just calculations that need to be done. This picture carries over completely, and this decomposition that you have, it's just that you're no longer over Z, you're going to be over a torus. You've got this more sophisticated family of line bundles. The connections exist as well, so we can twist. This works as well, but this is a difficult part because using the Borel-Bay here, there were tricks that we used basically to conclude that these bundles are positive or negative, which won't work in this setting because the representation theory is more complicated. This is a classical phenomenon. So showing that these bundles are positive and negative, this is problematic. And that would be a classical thing that happens almost. But there's also the bigger, more challenging, so more interesting, that this category that I defined before, relative half modules, which is the direct non-commutative generalization of the equivariant or homogeneous vector bundles. The calculi live inside here. They have a right and a left action. So in fact, they live inside here. But in the irreducible case, the right action here is very simple. somehow as easy as it could be. It comes from the fact that when I take the calculus omega 1, this is equal to OQ3 cotensor U QLS, like E star. The right action here is basically this one, because there's a trivial action on this. But when you go to the more general irreducible, the action here is no longer trivial. This is a purely quantum thing. It sort of has to happen by the commutation relations of these things. There has to be a non-trivial action here. It's just something that we don't see because the irreducibles are simpler. And then this correspondence between the category of UQLS modules and the action over here, this becomes much more complicated because this is no longer a monoidal equivalence in an easy way. So this is a big problem that we've been trying to figure out for a long time. I hoped when I was in Brussels that the category theorists, the monoidal category theorists would be able to do it, but they didn't. Kenny, the comma in the end, ran into the same problem with this, and he's since told me he's given up. So, I have an idea for Mauro, a paper on how maybe to look at this as well, but yeah, this is probably this and actually figuring out how to calculate how to show that it's positive here as well. Something like. But you know, we'll get there eventually.
Other questions? I have a quick question again then. So what is missing again from this being an actual spectral triple?
I mean, we just here we've got a lower bound for the spectrum. So this Fredholm property would be satisfied, but by a spectral triple, but definitely not the other way around. What we need is to look at the eigenvalues for this operator and show that the eigenvalues go to infinity as n goes to infinity. And that they have finite multiplicity.
And do you expect this to actually be a spectral triple?
Yeah.
And so
So if we knew the eigenvalues,
yeah,
if you had a description of the eigenvalues, then of course you can read off and you see that they go to infinity, and you can see that the multiplicity has to be less than infinity, and then you're done. All of the other conditions have already been taken care of. It's just this, but unfortunately at the moment to do this, we would need to explicitly calculate them, and explicitly calculating spectra is, even in the classical case, very difficult stuff, or just very tedious stuff as well. So then the idea with that I'm working on with RNAB is that one would relate the Laplacian of this to the Casimir inside in the enveloping algorithm. I guess I've also been looking at this with Shirazi and with Ale, so I should be careful since everybody's here. And then once you related this to the Casimir to calculate the spectrum of this is easy. Or at least to show that the eigenvalues go to infinity is just a basic representation theoretic argument. This is classically what's called the Partha-Shirati formula. Shirati. Patience, all right. So it's that's really how how we're trying to do it, is to relate this. And there's a lot of it's all algebraic and theoretic underneath it all.
And have you ever considered trying to maybe make a computer program that would do this, or putting Arnab in the basement and just locking the door for a year until he gets
program,
it?
No, the basement, sorry. No, I mean you can't calculate it by computer. I mean it's an infinite collection of eigenvalues, so there's nothing you can do. But this is, for example, when Freddie spoke about these things as well, that was where, together on a paper with Elmer, we did this for the B series irreducible. Of course, the B2 irreducible flag manifold. I already did it for CPN with Petter and Bishorup, but that's enough. More explicit calculation of spectra. The thing is to do is to get some sort of a conceptual connection between this and the Casimir. But that still involves quite a lot of calculation. That's why we were happy with this, because we actually did very little calculation, except for the Dolbeault, which is sort of a separate representation theoretically. By purely geometric arguments, one can argue that there is a lower bound. We don't know what this is, we never calculated it. But we know that it exists and it's related to the curvature of these line bundles, and hence that it gives the spectral gap in the Fredholm property.
If not, let's thank Ray again. We have Anna Duvenig from KU Leuven coming. So hope to see you there.